First off, new homework assignment. I know I was getting a lot of complaints that you weren't getting a homework assignment, so I thought, just kidding, nobody did that, except for, just kidding. Okay, so in this homework assignment, this should be a fun homework assignment. They're all fun, right? You all love doing them. Specifically, in this assignment, you will be breaking a crypto system. So you will be performing the role of a cryptanalyst. So what questions do you have? I mean, well, let's not say what you have. Okay, so like we talked about in the original, on Tuesday when we talked about breaking crypto system, you have the algorithm. The encryption algorithm is here in Python code. And there are two parts to this, two different tests. And you can get your personal ciphertext on the website. This will all make sense in a second. But first, before we dive into this, we will talk. Well, first, any questions on this? I mean, it's pretty straightforward. So what I want submitted is, so you'll need to submit the key. Make sense? Why do you need to submit the key?
Because that's how you break the encryption.
Yes, that's how you break the encryption, right? So, and submit your name, ASUID, plaintext, so decrypt it. So in your README file, include the plaintext that you discovered. Where did this plaintext come from? So do a little digging, figure out, was this just random stuff I typed in, figure it out. And if you use any code, which I encourage you to write some code. I think you could do this by hand, but that'd be a little crazy. I would not do that. So write some code in whatever language you're comfortable with. Again, I don't care. It doesn't have to submit and compile on our system. This is just whatever you wrote to help you break it. The code, so include your code in your submission and a description of how to use that code. So, I wrote a function to do this, to iterate over this thing and try these keys, and then I have these other functions to test which one's more likely, and an overall description of how you broke it. So, any questions on that? 2 parts, break stuff, have fun, due next Friday. So you got a little bit of time, is that right? Yeah, Friday. Questions? So some of you learned an important lesson on homework 1. Yeah, start early, I would say. Not just don't procrastinate, but start early. Especially with something like this where you're trying to break a crypto system. So what should be kind of some of your first steps? Panic. What? Panic? Yeah, start panicking now. Yeah.
Watch the recording of the previous lecture.
Yeah.
Make inspiration from how you broke the one you
Good. So look at the lectures. You could read the book to understand a different perspective on how to break a crypto system. What else? Yeah.
Figure out what the plain texts that are allowed and perhaps the keys that are allowed.
Exactly. So study this algorithm to try to understand what is it encrypting. What else did you try to figure out? Yeah, the function itself. How does this work? What is the encryption algorithm here? And this is key. So you should be able to use this, and you don't have to use this. If you don't know Python, don't use this Python. It's more or less pretty straightforward. I'm totally happy if somebody wants to post on the Piazza alternative implementations of this in other languages. That's totally cool as well. I don't really care about that so much. I don't care about that at all, really. It's more about just understanding this algorithm. So you should be able to encrypt things with it, decrypt things with it, understand how it works, and then you can progress from there to do some of the breaking style stuff that we talked about. Any questions on that? This is gonna be fun. Yes, exciting.
Do you have to use some sort of algorithm?
You have to break it. That's so, I don't know, if you get lucky and guess a key, you should put that here. I may be slightly skeptical of that, so you better have a good explanation for that. If you say like a magic fairy told you the key, that is also not acceptable. So really, I don't care how you do it, as long as you know how you did it and that you know how to do it. Does that make sense? No? Can't tell. You're being awful quiet. Are you already starting to panic? Wait to panic until after class. No need to
Are you
panic
saying
now.
that it's a bit difficult, or?
Am I saying? I'm not saying anything. I didn't say anything about difficulty. I'm just saying start. Don't start the day before. Like, you know, with a lot of, and this is a good, not just in general for coding assignments, but for things like this where you need to break something, is it easy to get stuck?
Yes.
Yes. And what do you do when you get stuck?
Give up.
No, you don't give up. Bad advice. Bad advice. You'll have a bad life. What do you do? Wait, we're talking about what to do when you get stuck.
You go to office hours, take a break.
Go to office hours, get help. So go to office hours. We will probably ask you more questions than give you answers, but that's okay.
Google.
That's the goal. Google, what else? Yeah. Piazza, you can ask questions on Piazza. What else?
Sleep on it.
Sleep on it. Yeah, you could just think about it. You ever think about a problem?
No.
No, you just start typing randomly and hoping things work out okay, right? And specifically about thinking about a problem, this is why if you have more time, you can take a couple hours a day off and then come back with fresh eyes. The other important things to do, reread the assignment description. There were many people for assignment 1 that just weren't implementing the spec correctly. Their logic actually was right, but they weren't following the specifications. And so by revisiting that, they just missed a critical part. So kind of with fresh eyes, revisiting the assignment description, with fresh eyes, revisiting how you're attempting to do this. I mean, these are all good, valid techniques to not get stuck. Getting stuck is normal. It happens for everyone, for all types of, especially I'd say on these like kind of hacking style assignments where it's, you're either gonna get it or you're not gonna get it. So the path you take, you may have to take multiple paths. The other key thing that I'll recommend is think like a scientist when you're trying to break these things in general. So what I mean by that is create a hypothesis. So if you're stuck, it means that you think your approach should work, but your approach does not work. Right? Similar to a homework assignment, when you submit it and you think I've done all of this and you only pass one test. Right? So at that point, there's either two possibilities. What are they?
The test is wrong.
Either the server's wrong and the test cases are wrong, or what?
Or your approach.
Or your code is wrong, or there's some assumption in your approach or your code that is wrong. So that's when you need to start thinking about, okay, what assumptions did I make? How can I test that I actually can do this? Some things to do would be, once you understand this algorithm, encrypt your own thing and try to reverse the key and break it from the ciphertext. Cool. Any questions? Yeah.
Are you just giving the ciphertext?
Yes. And the algorithm. So you have, just like we talked about, so you are what type of an adversary are you?
Ciphertext.
Ciphertext only adversary. So you get one ciphertext, you need to derive the key or break the key from that.
Base 64, is that C++ code?
We will get to that in 1 second, what base 64 is. Cool. Yeah.
So can we only submit once since it's already have the ciphertext?
Can you what?
Can we only submit once?
I don't remember. I need to look at it. I think you have multiple submissions, but it's, I don't know. Like you shouldn't be using the website to brute force the key. But you should be brute forcing it figuring it out on your own, right? And submitting actually is not working yet, but you can get the ciphertext from the site. Cool. Any other questions?
Okay, so
Yes.
on the submission site, it'll tell us, like, okay, so like it's not gonna be manually graded, it'll just be like automatic, like when you
Say it again?
like when we input our README file or whatever, like
Yeah, when you submit, there'll be a field for the key, and so you submit the key along with your files, and then it will tell you if you're incorrect or incorrect. And so assuming you're correct, everything goes good. At the end, after all your submissions are in, we'll read through all of them just to make sure that you actually, looks like you actually did it, and all that fun stuff. Any other questions? Yeah?
Well, this is being a hexadecimal form, you mean that it just needs to be written as hexadecimal?
Yes, exactly. So if you think the key is submit, and then we'll see and make sure that your key is correct. Cool. This will be fun. Yeah.
There's no submission link for this one.
Correct. It's not up yet. I will post it later. But you can get the ciphertext, so you can work on it. You'll know when you break it.
So the key is a certain decimal number or something?
You will have to figure that out from this algorithm. Yes.
Is the plaintext gibberish or is it in English?
I don't know. Figure it out. Would you be able to tell if you got it correct if it was gibberish or random?
Probably not.
Through the submission site.
Through the submission site.
No, that's not. You'll know when. Yeah. So that's when I don't tell you anything. You have to play the meta game of thinking, what am I likely to do to test you on this?
Give us
Am I going to just output random data, and
Yeah.
so you'll have no way of knowing exactly what it is when you decrypt it?
You just
I mean,
torture us for a week.
exactly. So depending on how horrible you think I am and how much I want you to suffer, then maybe you can think about which ones of those it is. Yeah.
For the previous assignment, did you add those father triplets in?
No, that will be done. You'll see grades. We'll do it after we do this assignment. I'll email you individually your grades, and that'll be a lot easier.
Oh yeah, and then how will we track our grades? Would it be on the submission website?
For this assignment or in
just
general?
Or just in general?
In general, I am more of a fan of emailing you directly your grades. So at various checkpoints throughout the semester, you'll each get an individual email that says, here are the grades we have for you on these assignments. So if you think there's any discrepancies, you let us know. That way you know where you stand, we know where you stand, everybody's happy. Cool. All right, let's dive in real quick. But first, we're going to talk about base 64. So, what is base 64? Does anybody know? Has anybody played with it before?
Just a base.
Just a number.
It uses ASCII.
So, if we don't know something, we go to Wikipedia and we figure it out. So, base 64 is a group of similar binary to text encoding schemes that represent binary data in an ASCII string format by translating it into a base 64 representation. So it's exactly what, so it is just like binary is base what?
2.
Base 2, hex is
16.
base 16, and so base 64 is base 64. So why is this useful? Why does this exist? Yeah.
For two reasons. To include different symbols, like if there's an exclamation point, or a period, or a semicolon, or whatever kind of symbols you need to get across your message, or an emoji.
There we go. So that's a good one. So actually, do I even know how to type those in? Let's see. Adam types emojis live. This is gonna be fun. Okay, so as soon as ever starts up. Okay, so I can type in hello. I can do Control D to end the input, and so it'll tell me that this is base 64 encoded hello, AGBV. And so if I take this, whoop. Hello. You all just broke it. Okay. That's not right. Okay. Okay. We will echo this and pipe it through base 64-D. And it says hello. So here I'm transmitting the message hello.
I'm assuming the assignment won't be that easy.
Again, you need to think about what you think I think is going to be. Okay, how? I'm going to do something really lame and just type in emoji. Oh no, that's a challenge. Okay, there we go. Can I paste this in? Wow. I'm actually shocked that this is working. Okay, cool. So now I can echo this and base 64 decode it. And it gives me the emoji. Wow, this is amazing. We are entering a new frontier of terribleness. Okay, so, but what are those actual characters, right? When we had hello, it was very simple. But how does the computer actually represent hello?
Binary.
Binary, right? In a sequence of bytes. So we can look at the ASCII table. which will tell us what each of the characters maps to in ASCII. Why is this so slow? And that's hex. There we go. So we can see this is the, there we go. So capital A is 41 in hexadecimal. So what we can do, if I do this, and instead of base64 decoding it, I output it to test. Okay, cool. So Hex Dump is a way for me to know what characters, what are the actual bytes in a file. So if I echo hello to test2, and I say hex dump test2, I'm looking at, if I look this up in the ASCII table, I have the bytes, and these bytes, hexadecimal that translate just to bits, 68, 65, 60, 60, 66F, and what's the 0A?
It's on the
New line,
terminator.
yeah, exactly. So it's a new line because echo, even though I didn't pass that in, automatically adds a new line. So if I cat and I print out test2, right, my terminal knows how to translate these bytes into these characters HELLO. So if similarly, our other, oh, that's not what I wanted. Oh, I see what I didn't do right. Okay. We will base64 decode it and then put that to test. So if we look at test, we can see that it has a very interesting F09F988B OA. So we know the OA is the new line again. These other characters are, and if we cat test, we'll see that awesome emoji. So it's very complicated. I'm not going to go into it, mostly because I don't understand all of the Unicode things. But basically, these 4 bytes represent that emoji when interpreted using Unicode. But if we just like yeah, what's okay, yeah. Anyways, you can learn all about Unicode code points, which we're definitely not going to go into. But the core idea is that to easily transmit the bytes that this emoji represents, right? F09F988B. One way to do that would be to base64 encode it. So turn that into a base64 representation, tell somebody else that it's base64, and so they can do what with it?
Decode.
Decode it back to the original bytes that I sent. And we can look at the Wikipedia page for base64, and we can see the exact table here of what everything means. I actually don't know base64 off the top of my head, so it doesn't really matter. But the point is base64 a crypto system?
Yes. No.
No.
Yes.
That's a lot of answers. Does anybody want to expand on one of those yeses or nos? I think one person's just going back and forth. Yeah.
There's no key.
There's no key? Why not?
I mean, you can say there's a key, but you cannot change the keys.
Ah, so what would the set of possible keys be? Empty set, right? There is no key. So if I send you a base64 message, can you decode it?
Yes.
Do I need to send you the key beforehand? No, similar, just like hex, right? If I said this byte has the hex value F0, do you need a special key to decode that? Yeah.
Well, isn't the key in a way kind of the mapping between the symbol and the numerical values? In a way?
Oh, sorry.
So, I mean,
Is the key a mapping? I would say that no, because it's part of the algorithm. So the key in crypto systems, the key exists outside the algorithm itself, and it's an input to the encryption function. But here we have the here we have I do need to tell you that it's base64 so you can decode it, but you don't need any additional information to decode that information. So this is great for if you want to share as text, like say an image file. Is an image file just printable?
yes.
You can,
Yeah.
you can print it to a printer, but into ASCII characters that you can just copy and paste.
Yes. I mean, not ASCII. Oh, I mean,
Yeah, not ASCII, right? So if you'd want to do that such that you can easily copy and paste in an ASCII string an image, one nice thing to do is to base 64 encode it. Or if you have any type of binary data you want to share such that it can be base 64, such that you want to share it to somebody to make sure they get the exact same thing, you'd use base 64. Yeah.
The Google text-to-speech outputs the speech in base 64, the audio.
Yes, so this is used all over the place, which is why I'm bringing it up and spending time on it, and also why we're using it here. So we can see that if we walk through this encryption function, the encryption function takes the clear text, does some stuff to it, and then takes the string to return, and base 64 encodes the string. So why is it doing that? Yeah. Exactly. So that when you go to the website and you get your ciphertext, if I just have random bytes, how do I display that on a web page such that you can easily put that into your program into a string? But here, and the other nice thing about base 64 is it doesn't care about new lines or spaces, so these new lines don't mean anything. So you can just copy this string, base 64 decode it, and then you have the exact bytes that the algorithm adds as input. Does that make sense? So this is really the way to think about it, is this is just a way to make transportation of that data easier. So don't let this part trip you up, because we just had a 10-minute conversation about it, 15-minute conversation.
What about the ORD function, the ORD function?
Yes, you'll have to figure that out. That's just the part I want to talk about, because it has nothing to do with the actual encryption itself. Okay. And now, does anybody know French?
Yes.
Can you pronounce this name?
Vigenère.
Vigenère, I will never be able to pronounce that right. Okay. I will try. So, we talked about the Caesar cipher. So what were some of the important things we learned about the Caesar cipher?
It was a bad cipher.
It's a bad cipher. Why is it a bad cipher?
Because it was easy
Easy
to decode.
to decode? How? Why?
Because it had a very simple base system. It had 26.
Yes, the key size, right? The set, if you think about, and this is what having formalism is nice, because we can say very specifically the set of k, or the cardinality of k, the number of possible keys is fairly small. It was 26, so we could easily enumerate all of those. So this was a similar idea, and I believe Vigenère, I already messed it up, was what actually came up with this other idea for this next crypto system. The idea is your key can be any size, and the way it's represented here is as a string. And what you're going to do is you can think of it as every element of that string. So let's actually just go through this. So we have, and sorry, my no beautiful drawings today because my tablet doesn't work yet for that. So that's not helpful. Okay, so we have the message, the plaintext message that we want to crypt. The boy has the ball, which is very security critical. And so what was the first thing we would do in a Caesar cipher? Huh?
Determine the key.
Determine the key. What else? Before we could even encrypt the message with a key.
So we take out the spaces.
Yeah, take out the spaces. Not a trick question. Right? We can't encrypt the spaces. And so the idea behind this cipher is we can have actually any length key we want. And what we're going to do, and we'll represent here the keys as letters. So we can do, let's say our key is, in this example, we'll do key is ABC, because that's going to be easy. So what we're going to do is go along the plaintext, repeat the key over and over, and shift each element of the original message by whatever the key is from essentially 0 to 26. So rather than have each key rather than have the key just be 0 through 26, we're going to represent this as a word, which is a lot easier to think about. But that just tells us the number of shifts to do. So we will repeat ABC, 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 and this doesn't work because we don't have monospace fonts. Format font. This is not useful. All right, new plan. There we go. Okay. And then, cool. Okay, slightly bigger. Okay, so similar information. So we have ABC, 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 ABC. And then what do we do at the end? A. Do we add a B? No, there's no more message. Cool. Okay, so what we're going to do is shift, for every A, we're going to shift the corresponding character in the message by 0. For B, it'll be 1. For C, 2, D, 3, but we don't have a D in our key. So for every one of those, we'll shift that message. So what's the first character of the ciphertext?
T.
T. What's the next one? I'm not going to do it. I have like 100 people here.
G. B.
Wait, B? Oh, B?
E. A.
So it wraps around.
H.
U,
What was it?
U,
U. Okay.
T, I, G, B, C, L, N, L.
Cool. So then, what do we transmit to the party we want to send this message to? Yeah, we need to transmit the key, just like always, right? We need to have some way to transfer the key to them securely so nobody else knows it. And then we transfer the ciphertext, and then what do? Yeah, the opposite. They subtract, right? So then they take the key, they do the same thing. They go ABC, 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 A, and then they will get the boy has the ball, hopefully, if that goes right. Yeah.
So what's the process again? You subtract T from A, like, and then
Should I go back this way?
no, just like the regular, like
So the regular one is you're shifting it forward. So you take T. So first you basically map every letter in the key, the key to a number. That tells you how much to shift it. So A is 0, B is 1, C is 2.
okay,
So this says take T, the first character, shift it by A,
which is 0.
0, so it's going to be T. And then take H, shift it by 1, which is going to be I. And then take E, shift it by C, and it's going to be G. Is this actually the key we use? Nope. Okay, cool. And so what's the benefit of this over the Caesar cipher?
More difficult to
Can't
brute
do
force it.
frequency
What was it?
More difficult to brute force it.
More difficult to brute force? Why?
because the
There's not
key is
just
not
26
just
26.
26. There's not
Yeah, how many? So let's say you know that the key is of length 3. How many do you have to brute force here?
26 times 3.
One second.
I can just,
26 times 3.
is it 2 to 3?
Yeah.
Right, because 26 tries with the first one, multiplied by 26 tries with the second one, times 26 tries with the third one. Anybody know that off the top of their head?
17,576.
Did you actually do that in your head?
No.
Okay, I was
That'd be impressive.
I'd be
I
very
read it.
worried and impressed.
I was able to read it.
So 17,000 tries. So could you do that by hand?
Yes.
Eventually.
I mean, eventually, yes. I guess the question is, how long is this going to take you to do this for every possibility, right? And so then what happens as we add more characters to the key?
It becomes more and more complex.
The key space grows more and more complex. So what about like a size 8. Could you do this
Yeah.
and finish before you die?
Yes.
Yes? You think you could do this?
Challenge.
Challenge? All right, $5 now. I don't think I could probably do that legally. Okay. Well, what's that? Yeah, 208 billion. There's no way you're going to be able to try all of those. And what if I have a 10-character key, right? This number just keeps growing exponentially larger. So if I want to increase the security here, I just add more keys. So do we agree this fixes the problem of key size?
Yep.
So what can't? I mean, so essentially, what we can't do is brute force the keys. Okay, let's look at another example of this, and we'll continue. Cool. So similar way, but with a different key of VIG, we can do the same thing, and we'll see that the ciphertext changes significantly. So now if we put ourselves in the shoes of the attacker, as we like to do, if I'm given this ciphertext, so we'll think about in decreasing order of attacker. So we, just like we did with the Caesar cipher of how to break it, so let's start with, we have the most powerful attacker, which is what? What was it? Chosen plaintext. So what plaintext do you want to choose here? Yeah, AAA is however long you think the key is. Why?
Just tells you what the key is.
Yeah, so let's say, so what I'm going to do is I take the key, ABC, 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 AB. This is actually more difficult than it looks. And then I shift each of the characters from the input that many down, so what's the result going to be?
A, B, C, A, B, C, A, B, C, A, B, C.
A, Z, Y. Because you're going backwards, it's going to be A, Z, Y.
Forward. So when we encrypt, we're going forward. So this is a chosen plaintext attack. So we choose the plaintext, so we're going to shift
Right, when you're shifting it back, when you're decrypting A, wouldn't it be A, Z, Y, A, Z, Y?
Well, so, okay, wait. So we have the chosen plaintext attack, right?
Yeah.
So we choose the A's. They're going to take their key, which we technically don't know, and then we're going to get this ciphertext.
Isn't the, oh, okay, yeah.
Like this ABC, ABC, ABC.
Gotcha.
So
yeah,
then
we're
how
not
do we
decrypting, we're encrypting it.
Exactly.
Gotcha.
Yes.
Is there like a version of this in crypto that's like backwards? So like you subtract it first and then you add it?
Possibly, but it's just a different crypto system, right? So again, if you assume that the adversary knows which one it is, it doesn't matter, because going backwards is just the same as going forwards, right? As long as you're doing the reverse, it's cool. So we get this, and then we get this ciphertext. So what's the key? Yeah, very simple, right? So we're able to easily break this if we can choose the message. So what about the other case where we don't get to choose the message? So if I gave you the boy has the ball and this TIG BPA HBUTIG BBNL, could you get the key?
Part of it.
Yes.
So you subtract it. So what's T minus T? A. And what's H? I minus H? Or H minus I?
Should be A, B, C,
Right? So now, so if I know the plaintext, I can easily recover the key from the ciphertext, right? So we still didn't fix the problem against a chosen plaintext adversary and a known plaintext adversary. But what about just what about an adversary that just has this?
Probably like analysis, because TIG is lead and it repeats once.
So let's first stop and think. The first thing we should think about is applying our previous techniques against this new technique. So then what happens if so what did we do before? Okay, we brute forced it one way. We don't want to brute force it because there's 17,000 tries for here. What was it? Frequency analysis, right? So what we did is we looked at the frequency of each letter and we compared that with the English language. What's that going to show here?
Gibberish. I mean, uniform distribution.
Yeah, why a uniform distribution? Or
Because we assume the key is chosen at random, uniformly.
right, so think about this. Why in a Caesar cipher did the frequency of the English language, the characters in the English language remain the same? Yeah.
Every I becomes the same.
Right, so that entire graph is just shifted, right? Because every character is just moved a fixed amount. But here, what does the shift depend on? Not just the key. I mean, it does depend on the key, but what else? What was it?
How long is the key?
How long the key is?
Which letter in the key it
Which letter, the position of the, the position of the character in the message, right?
Modulo the length of the key.
Exactly, modulo the length of the key, right? So, so if we, cool. So if we look at this, we could use our frequency analysis of this one, and we'd say that it's using, if we tried to break this as a Caesar cipher, we'd say, well, using the techniques we talked about on Tuesday, maybe a likely key is 22, which we try and it's this, or maybe a key likely is 10 and it's this, or maybe a key that's likely is 4 and it's this. And you can do this for all of these, and are you ever going to find the message? No, because fundamentally there's no way to get back to that message using a one-key Caesar cipher. So a couple things, and actually as we'll see when we eventually get there, and we'll try to think about this. So we're going to define some terms. So one thing is the period, which is the length of the key. So think about like a pendulum in physics, right? The period is the time. Here is essentially the time that the key repeats over the message. Okay, cool. So how can we break this? Yeah.
Maybe insert our own message.
We can't insert our own message. So here we're only chosen ciphertext. This is all we have. You have this TIG BPA HBU TIG BBNL.
Do we know the length of the key?
Let's say we don't even know. Well, okay, we'll start first. Assume we know the length of the key. So we know it's length 3.
So we should break up this string into groups of 3, perhaps.
Why would we break up the string into groups of 3? So what would that mean? Like this? Like TIG BPA
Yeah.
HBU TIG BBNL or BBN and then L?
Yes.
Why?
We
Because-
can do a frequency.
Sorry, what?
Because you know that if the key's of length 3, then it's just repeated on each of these.
Okay, if the key's of length 3, then we know that the key's been repeated there. How does that help us? Yeah, so okay.
We can do a frequency analysis on each position then.
So now we know that the first character of all of these are encrypted with what?
The same.
Same.
It's a Caesar.
The same letter. So this is a Caesar cipher just on these first letters, right? On essentially here we have TBHTBL. So these are all essentially, I can't spell Caesar, is that right? We'll go like this. Yeah, with the first letter of the key, and so we could do IB, IP, BIB, is that right? And that's with key 1, GAUGN, and that's with key 2. So then what do we know about each of these letters? So we know that they've been encrypted with the same key. So then what does that tell us?
That they have the same offset.
They have the same offset? Yep.
They're 2 positions away from each other.
They're every third position.
And we
The length is a third of the.
What was it?
Can't we just do the analysis now on each one of them?
So what kind of analysis? What do you want to
Or
do?
the letter analysis, the same thing, like count how many.
Yeah, so then we can do frequency analysis because we know each of these letters have been shifted the same amount. So they should each have a different shift. So essentially, now how many Caesar ciphers do we have to solve? 3. Right? So we can solve each of these. Are they connected? Can we use techniques like I think last time we used techniques of looking for like a THE or using in the ciphertext itself? Can we use the fact that this B and this B follow each other? Why not?
Different Caesar.
They've been encrypted with different keys, right? They've been shifted by different keys. So the fact that these two letters are the same in the ciphertext just because they're next to each other tells us nothing. But once we're able to figure out one of these keys and we know that it's correct, then what can we do?
Then we can just start guessing better.
Yeah, then we can, if we think, okay, we think we know maybe we have more characters here, we get a frequency distribution, and we say, oh, this is likely encrypted with A, right, which means it's not shifted at all. Now you know these characters, and then maybe you can start guessing the other keys based off of that one. So you say, oh, I know this first one is a T, I wonder if this is like, and then you maybe break the third one and figure out that that this character is an E because it's shifted forward 2. And you say, well, it's probably highly likely that this is THE. So you know the second set here. Yeah.
Is it also like, because I think someone said we have like a repeated like TIG as well. Is that, can we also use that?
Yes. So let's. We could definitely use that. So yeah, especially when we group this up here, we'd say, well, TIG and TIG are the same. So that means in the message, those letters must be the same. So yeah, you can think about 3-letter words and trying to guess it based on this. The thing I want to talk about now is, what if we don't know that it's, so we knew to split this up into 3 different alphabets. Why?
We knew the length.
We knew that the key was length 3. What if we don't know? Yeah.
Could we, kind of going on what we just said, we saw TIG and TIG repeated in sequence. Could we look for stuff like that as well?
Right, so we can look for repeated characters and see, but these repeated characters are, let's see, what is it? This T is 1, 2, 3, 4, 5, 6, 7, 8, 9 characters away from the other one. So should we guess that the key is length 9 or 8?
No, but we might be able to guess like that chunk of the key.
Or we know that, so if we think about what are the possibilities that these characters ended up the same, means it's likely that parts of the key went over to characters that were the same in the ciphertext. Otherwise, those characters would essentially be random. So we'd know that one of the things we'd look for is, so we'd look for repetitions like this. We could say, okay, I know TIG is repeated, so I know that the length is probably a factor of 9. It could be 9 itself, or it could be 3. How could we guarantee that how do we know that it's not 1? That the key is of size 1?
Because then it would be a normal Caesar cipher.
It'd be a Caesar cipher, right? And we could tell based on the frequency. We could calculate the frequency and see that, wow, it's pretty random. So we could try this. We could look for, are there any other repetitions in here?
TIGB, that's all.
Yeah, so we actually have TIGB, right? Which is TIGB and TIGB, which is also 9. Is that right? So it could be 9 or 3. Do we now have more confidence that? Yeah, it's probably definitely 9 or 3 because we have more characters matching, right? So it's rather than just a randomly occurring because of the way the shifts worked out, it's highly likely that those characters are repeated. So we can look at that. We'll look at some other ways to do it. But essentially, you just figured out how to solve a Vigenère cipher. And this is the fundamental approach. So first, figure out the length of the key. And then once you have the length of the key, you know what to do. You split each of the characters up into its own alphabet. Each of those is essentially a Caesar cipher. And you break each of them individually. So we'll walk through that. But this is the core idea. You all just figured this out. Good job. Cool. So if we're given some random stuff, and here I've just, the spaces here don't matter, I've just split it up into groups of 5 just to make it a little bit easier. And so this is the, I guess, this person was, I guess, the first person to figure out that these repetitions of ciphertext occur when characters of the key appeared over the same characters in the ciphertext, or at least it's highly likely. And we already saw that here, but this is just a different key, right? This was VIG instead of ABC. But we can still see that same ciphertext. And so this is exactly what we talked about. So we take the distance between the repetitions, 9, and we say it's likely that the period is a factor of 9. So 1, 3, or 9. And so we can do the same thing here. So does anybody notice any repetitions? What was it? EQ. Are you just shouting out random letters?
No, it's second column, third row.
Second column. EQOOG. That's good. Okay. EQOOG.
And then
where on
first column, second row.
Second.
Oh, here. Oh, good. EQOOG. Anything else?
Are we assuming that the length is 5? Key length?
Yeah, that length is 5. That's pretty big. We'll just go look at this because you'd want to look at kind of all of them. So you'd see MI repeated, OO, and actually the EQOOG actually has an O at the beginning, so it extends longer. MOC is the other second longest. And so you'd figure out the distance, figure out the factors. So based on this, what's a likely key size? 3, 2. So what are the possibilities based on these factors? 2, 3,
11.
5. What was it? What was it? 7, 11, and also all the combinations of these. So 22, 15, 10. Also 6. Why 6?
3 times
2 times 3. So what do you want to, what would you, if you were gonna, you had one shot or you're trying to maximize your time, because you don't want to, probably 6, why? Because, so A, we want to make sure whatever we test first is a factor of the longest repetition. Why?
Because it's more likely to be repeated.
Yeah, a long repetition is less likely to occur due to chance. These repetitions could happen just because of the way the key ends up and the way the ciphertext ends up. It doesn't necessarily mean that the ciphertext is the same. So we definitely want to try 2, 3, 6, 10, 15. I already did 10, 30, and 30. I mean, we think 30 would be kind of crazy. That's pretty long and compared to our ciphertext. And then we look at the other ones and we say, okay, what matches, like what of all those factors matches roughly with the most of the other repetitions? 2 and 3, or 6, right? So yeah, you'd think we could try that. There's some that won't work, but that's kind of the way it goes. So it could be any of these. So this is exactly the analysis we just did. And we could even calculate how many of the others have. So 7 out of 10 have 2 in their factors. almost as many, so 6 out of 10 have 3 in their factors. So we could try 6 based on this. Now, do we want to split this up in, how do we actually verify our guess? Like, do you want to then split these up into alphabets and then try to solve each of them individually? What if you guessed the key wrong? You just wasted a lot of time. I'm trying to save you time. So what do we do? So let's think about, and to think about that, let's go back to here. So what if we guess a period of 2?
Isn't that
Will we ever get it?
no?
No. But how can I tell?
Couldn't you tell after the first few characters?
After the first few characters, so what I could do is split it up just like we did. So T, I, G, B, P, A, H, B, U, T. So can you tell I'm on the wrong track right now? Because I can't. Yeah, there's no repetitions, but I don't know, maybe the message isn't that long. It says a word is repeated in a, what is this, 10 characters or something? 15?
16.
How did we break this? Or how did we, when we guessed period 3, how did we break this? Yeah.
None of the characters is the same, which seems like it would be odd. So
Why? Why is that odd?
an English message would probably repeat some of the letters.
Because of
It has to be the letters in exactly the same positions, right? Because it's every, in this example, we took every 3rd character into the same alphabet. I mean, you could say, well, the odds of that occurring are however long it is divided by the key or something. What's also weird about not having any repeated characters?
yeah.
Every character has the exact same frequency. Does that match with the English language? No. How did we break it in this when we guessed period 3?
Frequency analysis.
We use frequency analysis. We can map the frequency of each of the characters and try to map that to English. But when we do that here, our frequencies essentially become random. So this is the idea that we can use for this is, and it's based on kind of your intuition, is essentially how random are the characters in our alphabet? Are they close to English or are they not close to English? And if we guess wrong, it should be essentially random, those characters in each of our alphabets. Does that make sense? Questions? This is definitely a good, this is the kind of check yourself moment you want to do so that you don't spend time trying to break a cipher when you have the period wrong. Because that's just, you're asking for trouble. Cool. Okay. So, we're going to define a term to help us kind of quantify this. And this is the index of coincidence. So it's the probability that 2 randomly chosen letters from the ciphertext will be the same. So what does that mean? So if it's English and you randomly choose 2 letters, so let's say the opposite. So you have a completely random input, random characters. You grab one character, what's the likelihood that you grab another and it's the same?
1/26.
Yeah, 1 out of 26, right? Because that's the probability. It's just a completely random whatever you're going to get. So let's say it's English. You grab one character and you grab another. Is it going to be 1 out of 26 that they're the same?
No.
Why not?
Because the frequency for those letters.
The frequency of the letters changes, right? Is different. And you can think about it as kind of, so, and this was, in some sense, the key problem with the Caesar ciphers. We had this distribution of English that just got transferred or moved around, right? It got shifted. So we say we add we add an extra character to kind of shift some characters by some and some characters by another. So the idea is if you only have a period of 2, you can actually calculate how much from English the index of coincidence deviates. And so you can find tables of this online. So for 1, it's the index of coincidence once you calculate it is, I don't know, on average 0.066. For a period of 3, it's 0.047. For 5, it's 0.044. And you can see, hopefully, that it's approaching 1 over 26, which is, I believe, what it's doing. Is that right? 1 over 26. Yeah, which is 0.038. Can you see that? Yep. So as the period increases, it's essentially random. Does that make sense? Right, because each character in the ciphertext is just moved a complete amount. There's no relation between them at all. So there's a couple different ways we can do this. We can, and so this is computing the index of coincidence. I'm not really going to go into how to do this. It's just a mathematical formula. We can break it down very quickly. So you take the n is the length of your ciphertext. Fi is the frequency, the number of times that I occurs in the ciphertext. So you go through all the letters. So this 0 through 25 is all the letters. So you say, how much what's the frequency of A in the text? And so you'd say the frequency of A times the frequency of A minus 1. Add that to the frequency of B times the frequency of B minus 1. And keep going with that. Divide all of that by the length times the length minus 1. At some point I did know how to derive this, but I honestly don't think it's that important. So we can compute the index of coincidence for our original example here. And if we do that, we'll get 0.043, which is about where? Around, 5 or kind of between 5 and 10. I mean, you're talking about, so this is why you don't want to use this just as your initial thing to tell you exactly where to go. A, this is based on a lot of data, and B, the granularity here. I mean, look at the difference between 4 and 10. Very, very small, right? And it could just be weirdness, or you could get lucky. So you just kind of want to use this as a check. So this roughly tells us that our period is between 5 and 10. Does that jive with our guess? Which was 6. So we'd say, okay, that's awesome. So this agrees, so that's good. And then when we go and we split our alphabets up, if we calculate the index of coincidence on each of these alphabets, so if we go back to our old example, what should be the index of coincidence for this alphabet? What's the period of this?
1 or 0 or
1. Why 1?
Each individual character is shifted.
Yeah, each individual character is shifted the same amount, right? It's a Caesar cipher. Right? You can think of a Caesar cipher as essentially just a subset of an array cipher where the key size is 1. So here now we have a bunch of these. So if we calculate the index of coincidence, they should be all roughly around 1. So what would the index of coincidences be for these alphabets when we said the period was 2?
None of them are the same?
Not 0. We could still calculate it, although that's interesting. Actually, don't know what it'd be in this case. But in the general case, what would we kind of expect?
Significantly off from 1?
Significantly off from 1, and probably closer to random, because we're essentially pulling characters at random that were shifted with different keys. So they could be, and each character of the key, assuming a random key, is completely unrelated to each other. So we're essentially just pulling random characters together. So we should get something close to 1 over 26. And so this is how we can use this. So this is why this index of coincidence is awesome, because we can use it in two different ways. One, to verify our period. Does the period actually match with what we expect based on what we calculated on repetitions? Here it's roughly the same. And then after we split it up into 6 different alphabets, we can then calculate an index of coincidence for each of those alphabets, which should be close to 1, right, with the period of 1 of the English language. It's actually kind of very similar to thinking about looking at the distribution of characters and comparing it to English. It's another type of measure for that. So we could do that. So these are every 6th character. So the first character, the 6th, all right, 7th character maybe. This is the first alphabet, so we can see the index of coincidence, if we calculate it, is 0.069, which suggests a period of what? 1. Oh. And then we'll do that for the other one, 0.078, 78, 56, 124. Ooh, this one is 0.043. Should we be worried?
Not really, because the other one.
Yeah, not necessarily, right? It's something that we'd be keeping in mind, right? Our previous measure checked. A lot of them are very close to, and this one's also very high. I don't know why. I mean, it's random, essentially, right? So these are just approximate measures. Nothing's going to match exactly, especially with a small alphabet, right? Because from the original ciphertext, how much of each of these do we now have?
A 6th of it?
A 6th of it, right? So now our sample size of samples to draw from is smaller, so we'd expect a kind of higher variation in these values. But if they were all close to 1/26, we'd say, man, I messed up. We should restart from the beginning. And then we solve, just like we did in the Caesar's case. And so just like in the Caesar cipher, we can, so can we just brute force each character? So now we have it, because this is how we solved the Caesar cipher, right? We just brute forced all 26 possible keys. Can we do that here? For each alphabet? Okay, so brute force that first alphabet. What's the key? How do you know if you're right?
You just brute force like the few for each alphabets and then see if that gives you something.
So why do you need to brute force 3 alphabets?
Not necessarily 3, but like if you
Why can't you do it on 1? That's what we did on the Caesar cipher.
because this is just like random. This is every 6th letter.
Yes, exactly. So it's every 6th letter, right? So previously, if I can ever find it, previously we were able to use the positions of the characters, right? So when we shifted, we knew that when we saw English, because we get, now the message makes sense, it's actually English. But here, if you just magically were able to get, like, how do you know that every 6th character is English? Do you? Like, how do you know when that's actually English? Yeah.
Will it match the frequency analysis of English?
Right, so you can try to do that, but how do you know that you're right? Because in the Caesar cipher, we could say, okay, match the frequency analysis, and then we'd say, bang, we got it. It's English. Let's say you shift the distribution such that it matches English. How do you know for every 6th character if it's actually English? You don't. You fundamentally don't. It's very difficult to be able to tell right away that you got one part of the alphabet. Because you may get, when we broke that, there may be a couple shifts that are actually pretty good, right? So you don't know which one it is. So a common technique is you're trying to use, so you basically guess in some sense. So this is why you can do this by hand. It's a little tedious, but you can do it. Writing a program to do this is very nice. And so this is kind of basically a way of doing frequency analysis. So in this case, rather than doing the frequency of every character and calculating that value and figuring out which shift we want to do, here we're just counting up what's the number of times that each of these characters appears in that alphabet's ciphertext. So we can look at for all of these. And so we could probably say something like, is the fourth alphabet at the right shift? Like in English, is there a lot of, do you frequently encounter a lot of W's, X, a lot of X's, Y's, and Z's? No, so this is definitely not at the right shift. And what we could do is we could, and this is kind of a kind of cheating by hand version, is this is rather than that precise graph of all of the letter frequencies of English, here we're just putting high, medium, or low for all of the characters. And so we can roughly see, so like what, based on this, what kind of should the shift be for 1? Three or four. So if we shift it, what, back? 4, 1, 2, 3, 4. So that becomes 1, 2, 3, 4. So that would mean there was a lot of W's in this text. What do you think? 6. 6? A shift of 6? Where is the shift of 6? One, two, three, 4, 5, 6. So I would put this back. 1, 2, 3, 4, 5, 6. 1, 1, 1, 1, 3. So then one of the most frequent characters then becomes C, which is only has a medium frequency. What was it?
No shift on the first one?
No shift. Why no shift?
Because A is frequent, E is frequent, and then O is frequent.
So A is frequent, E is frequent, high, high.
I and
O is frequent, which is high.
and I.
And I is also frequent. So it seems like a reasonable thing to say. Maybe this was no shift. Does it completely ruin the? So it's. I don't think we talked about it explicitly, but it's pretty easy to reason to yourself that a no shift of a Caesar cipher, a key of 0, is terrible. Why?
Plaintext.
Yes, it's the plaintext. The plaintext and the message are exactly the same, right? But in here, do we have that similar problem? No, not necessarily, right? Because even though the shift is 0, we have a whole bunch of other shifts that are shifting those characters around. So, okay, cool. So we'd kind of go through that and we'd say, okay, what if we assume that this first alphabet has a shift of 0? We could also maybe see, I think 5 here. This one stands out to me because of the, let's see. It stands out because of the 5 C's here. So what would I do? I would, and then the 5 M's. So it's probably likely that one of these is an A and one of those is an E. Does that make sense? No.
No.
It's not. Maybe one is an E.
A and O.
A and O? Oh, okay. It's already O. Yeah. So, anyways, we can play with this, try to figure out what some of these things are. This third alphabet, if, what does it say? If I shifts to A, so you have A, B, C, D, E, so that's kind of nice. You have the two A's, 4 E's. You could try to make some guesses, essentially, and then start substituting and start seeing, okay, from the ones that you can guess, now we can use our knowledge about what are likely 2 grams, so 2 character sequences, what are frequent 2 character sequences, and 3 character sequences to try to decipher. So we could look for various clues here. So basically in bold here we now have all of the ones that we think are correct. You'll have to go with this on your own, but you start guessing alphabet by alphabet. Once you have a guess, now you've got more of that alphabet. And then you can keep, I don't agree with kind of any of these things, like none of these are obvious to me. Except for I mean, the other thing you'd look for is like I'm pretty bad at these kind of things, but you can code stuff to do this for you, so you don't actually need to do it, which is nice. And computers are a lot better at guessing than you are. So then once you're here, you can start to brute force or start to pick out words and figure out what the eventual thing is. So here you could use, and this is something that I guess I have used before. So if you know that there's a Q somewhere, the letter following it should be a what?
U.
A U. That would be the first thing to try. And so then you get this terrible limerick, which is a limerick packs laughs. Whatever, you can figure it out later. I'm not going to read it. I will lay you out. Good stuff. Look at that. We're breaking ciphers every day. Huh. That's bad. Wait, just a
For text. There's a next line on the end of each line.